I thank you all for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of July 2024. This question is from the section Linear Algebra and it is pertaining to the concepts of quadratic forms. This question is from the part C, a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704078. Right. The given question is, let Q1 of x1 comma x2 and Q2 of y1 comma y2 be real quadratic forms such that there exists ordered pairs u1 comma u2 and v1 comma v2 belongs to R square such that q1 of u1 comma u2 is 1 is equal to q2 of v1 comma v2. We are given two quadratic forms q1 and q2, right, and it is further given there exists ordered pairs u1 comma u2 and v1 comma v2 belongs to R square such that q1 of u1 comma u2 is equal to q2 of v1 comma v2 is equal to 1 at these two ordered pairs. Define q of x1 comma x2 comma y1 comma y2, a 4 tuple, is equal to q1 of x1 comma x2 minus q2 of y1 comma y2. Which of the following statements are necessarily true? We are given 4 options. Option 1, Q is a quadratic form in x1, x2, y1, y2. Option 2, there exists an ordered pair t1 comma t2 belongs to R square such that q1 of t1 comma t2 is equal to 5. Option 3, there does not exist an ordered pair s1 comma s2 belongs to R square such that q2 of s1 comma s2 is equal to minus 5. Option 4, given an alpha belongs to R, there exists a vector omega belongs to R to the power of 4 such that q of omega is equal to alpha. Let us now discuss the solution of the problem in detail. We have two real quadratic forms, q1 of x1 comma x2 and q2 of y1 comma y2. Let q1 of x1 comma x2 is equal to x transpose ax, x is capital X, and q2 of y1 comma y2 is y transpose by, where A and B are 2 by 2 real symmetric matrices, where A is equal to A11, A12, A12, A22, right? In the place of A21, we have A12 because it is a real symmetric matrix. B is equal to B11, B12. In the place of B21, we have written B12 because B is symmetric. B22 are 2 by 2 real symmetric matrices. And what is capital X? Capital X is the column vector x1, x2, and capital Y is the column vector y1, y2. Right. Q1 of x1 comma x2 is x transpose AX is equal to, when expanded, you will get a11 x1 square plus 2a12 x12 plus a22 into x2 square, a quadratic form, right? And Q2 y1 y2 is y transpose by is b11 y1 square plus 2b12 y12 plus b22 y2 square. It is the next second quadratic form. We are given, it is defined Q of x1, x2, y1, y2, a quadruple, is equal to Q1 of x1, x2 minus Q2 of y1, y2. Write down Q1 of x1, x2. So now we call on option 1. Option 1 says Q is a quadratic form in 4 variables x1, x2, y1, y2. Now we have, it is defined Q of x1, x2, y1, y2 is equal to Q1 of x1, x2 minus Q2 of y1, y2. Q1 of x1, x2. For that, we write that quadratic form. a11 x1 square plus 2a12 x1, x2 plus a22 x2 square minus Q2 of y1, y2. That quadratic form we write, that is b11 in brackets b11 y1 square plus 2b12 y1, y2 plus b22 y2 square. Now, what is this? It is a quadratic form in 4 variables x1, x2, y1, y2. It is a homogeneous, polynomial, homogeneous polynomial of degree 2 in 4 variables. It's a homogeneous polynomial of degree 2 in 4 variables x1, x2, y1, y2. That is precisely the definition of the quadratic form. So therefore, this is clearly Q is a quadratic form in x1, x2, y1, y2 because every term is of degree 2. Right. So the option 1 is true. Right. We move on to the next options in the next slide. Right. We are given that there exists ordered pairs u1, u2, v1, v2 belongs to R square such that q1 of u1, u2 is equal to q2 of v1, v2. We now establish an intermediate result. That is a result in between these two. So what we want, we claim q1 of RU1, RU2 is equal to q2 of RV1, RV2 is equal to R square for all real numbers R, small r. It is very simple, but we require this. We have, there exists ordered pair u1, u2 belongs to R square such that q1 of u1, u2 is equal to 1. This is given to us. Now, let R be any real number. Then q1 of RU1, RU2 is equal to the RU1, RU2, that is the row vector RU1, RU2, A into column vector RU1, RU2. When you multiply, R will come from the row vector and another R will come from the column vector. They will come out, and that is R square into U1, U2 ordered pair multiplied by A into the column vector U1, U2. That is precisely R square into Q1 of U1, U2. But Q1 of U1, U2 is 1. So R square into 1 is R square. Thus we got this result. That is the first one. And similarly, you can do it for Q2. Q2 of RV1, RV2 is equal to R square. Okay, this is what we want. It is an intermediary result. This we will use in the next slide. Right. We call option 2. There exists T1, T2 belongs to R square such that Q1 of T1 comma T2 is equal to 5. In the above, in the Q1 of RU1, RU2, that we have shown it to be R square, you take R is equal to root 5. Q1 of root 5 U1 comma root 5 U2 will be equal to root 5 square, that is 5. So T1, T2 is ordered pair, T1, T2 is ordered pair RU1 comma RU2. So there exists, yes. So let T1 is equal to root 5 U1, T2 is equal to root 5 U2. Then Q1 of T1 comma T2 is equal to Q1 of root 5 U1 comma root 5 U2 is equal to root 5 square, that is 5. So thus there exists ordered pair T1 comma T2 belongs to R square such that the value of the quadratic form Q1 at T1 comma T2 is equal to 5. Thus the option 2 is true. We call on option 3. There does not exist an ordered pair S1 comma S2 belongs to R square such that the value of Q2 at S1 comma S2 ordered pair is minus 5. There exists ordered pair such that this happens. So that means you have to identify a quadratic form wherein this is true. So for that, consider the quadratic form Q2 of y1 comma y2 is equal to y1 square minus y2 square. Yeah, Q2 of 1 comma 0 is 1. Yes, there exists an ordered pair v1 v2 such that Q2 of v1 v2 is equal to 1. So this is satisfied. Right. Now for 0 comma root 5 belongs to R square, we have Q2. The value of Q2, the quadratic form at 0 comma root 5 is equal to, substitute in this y1 square minus y2 square, y1 is equal to 0, y2 is equal to root 5, substitute. So 0 square minus root 5 square, that is minus 5. This happens. So there exists. So thus there exists S1, S2 is equal to 0 comma root 5 belongs to R square such that Q2 of S1 comma S2 is minus 5. Such a quadratic form exists. Agreed. Therefore, the option 3 is not true because there does not exist, it is given, but there exists. So therefore, option 3 is not true. We move on to option 4. So given alpha belongs to R, alpha is any real number, there exists a vector omega belongs to R power 4 such that Q, the value of Q at this omega is equal to alpha. Now, for any R comma S belongs to positive real numbers, we have Q1 of root R U1 comma root R U2 is equal to root R square, that is R. Q2 of root S V1 comma root S V2 is S. Agreed. When R and S are positive, that is why roots are taken. Right. We have Q of x1 comma x2 comma y1 comma y2 is equal to Q1 at x1 comma x2 minus Q2 at y1 comma y2. Q1 of x1 comma x2 minus Q2 of y1 comma y2. Let alpha be any real number. So first case, let alpha be greater than or equal to 0. Then you can talk about root alpha in that case. Then Q is equal Q of root alpha U1 comma root alpha u2 comma 0 comma 0 is equal to q1 of root alpha u1 comma root alpha u2, yes, q1 x1 x2 minus q2 y1 y2, that is 0 comma 0, and q2 0 comma 0 is, put r is equal to 0 here, it is 0, and q1 of root alpha u1 comma root alpha u2 is root alpha square, that is alpha minus 0, that is equal to alpha. Thus for any alpha greater than or equal to 0, there exists a vector omega that is equal to root alpha u1 comma root alpha u2 comma 0 belongs to r power 4 such that the value of q at omega is alpha. Now let alpha be negative. When alpha is negative, minus alpha is positive, then you can talk about root of minus alpha. Then q of 0 comma 0 root of minus alpha v1 comma root of minus alpha v2 is equal to q1 of 0 comma 0 minus q2 of under the square root of minus alpha v1 comma under the square root of minus alpha v2, and q1 of 0 comma 0 is 0, put r is equal to 0 in this, and minus q2 of root of minus alpha v1 comma root of minus alpha v2 is root of minus alpha square, that is minus alpha. So that will be 0 of 0 minus of minus alpha, that is equal to alpha. For alpha negative, there exists a vector omega that is equal to 0 comma 0 comma 0 comma root of minus alpha v1 comma root of minus alpha v2 belongs to r power 4 such that q at omega is equal to alpha. So combining these two cases, for any alpha belongs to r, there exists a vector omega belongs to r to the power of 4 such that q at omega is equal to alpha. Thus, the option 4 is true. So, the answer to this question is options 1, 2, 4. Option 3 was not true. Right. And that is the detailed discussion of solution of the problem, given problem in the examination from the section linear algebra, which is related to the concepts of quadratic forms. It is definitely a very good question, and it will be a difficult problem in the examination. Right. I am sure that you have understood the solution of this problem. I thank you all for watching my video. Please like my videos and share them with your colleagues and friends. Please subscribe my channel if you have not already subscribed. I wish you all the best. Thank you.